Everybody, today we're going to look at a rate of change question. So we have the cost per hour of a train that is going at some speed v, and its cost function is modeled by this function here, c of v, where the cost is measured in dollars and the speed v is measured in kilometers per hour. So first off, we're asked to find the cost of running the train for 3 hours at a speed of 100 kilometers an hour. So let's just go ahead, and now this is the cost per hour, right? For any given speed that this train is running consistently at. And so the cost per hour for a speed of 100, right? Because again, v is measured in kilometers an hour. So 100 kilometers an hour means a v value of 100. And this is again the cost per hour. And so to find out the cost running the train at this speed for 3 hours, we're simply going to multiply this by 3. We can even do a 3 at the beginning, right? And so that's going to mean 3 times c of 100, right? So we're going to plug in 100 in for v, and so we'll have 100 squared over 20 plus 50,000 over 100. And so that'll be 3 times, that's 10,000 over 20. That's 5,000, that's 500. So we're looking at 500 plus 500 again. That worked out well. And that's 3 times 1,000 for a total of $3,000. So to run this train for 3 hours at a constant speed of 100 kilometers an hour, we're looking at a cost of $3,000. Now for part B, find the rate of change, right? That is what our first derivative gives us in the cost for trains going 100 kilometers an hour. So if we want to know the rate of change at a specific point in time, we're going to look for the derivative of the cost function, meaning we're going to look for c prime of v. And so now we can differentiate the way we always have. So using the power rule, the 2 multiplies out front, 2 over 20 simplifies to 1 over 10. And so we'll have just v over 10. Now, you know the derivative of 1 over v is negative 1 over v squared, right? That's one of our classic derivatives. And so that means this is going to become negative 50,000 over v squared at v is equal to, once again, 100. And so that means that we're looking for the derivative function evaluated at v is 100, meaning we want c prime at 100. And so let's just plug that value in for v. So in c prime of v, we'll have 100 over 10 minus 50,000 over 100 squared. And that will be 100 over 10 is 10 minus 100 squared is 10,000. 50,000 over 10,000 is 5. And so 10 minus 5 is 5. So this is the rate of change in the cost for trains going at 100 kilometers an hour. So that means that the cost is going up by $5 per kilometer per hour increase, something like that. And then part C, we're asked at what speed is the cost function minimized, right? So at what speed is this cost function at a minimum? We can try to sketch that. You can pop this on Desmos, kind of get a sense of where the minimum point lies. Or we can simply look at when our derivative gives us a critical point, i.e. when our derivative c prime of v is equal to 0. And then we can do a second derivative test or sign analysis to figure out whether that critical point is a max or a minimum, right? So if we set this equation equal to 0, we're going to have v over 10 minus 50,000 over v squared set equal to 0, right? Now, here I'll contrast with different colors. So let's move that over. So v over 10 is equal to 50,000 over v squared, right? And so now we can cross multiply, as you might have learned to do. So that means that we get v cubed is equal to 500,000. And now taking the cube root of both sides, we're going to get a value of v that is the cube root of 500,000. And the cube root of 500,000, that's 5 times 10 to the power 5. I don't know that off the top of my head. Let's pop that into a calculator. What is the cube root of 500,000? You can also raise that to a power of 1/3. If you don't have a cube root button, that's 79.37. 79.37, and this is the velocity v, and so we should have our units of kilometers an hour. And since this is a unique solution, we can probably assume that this is indeed a minimum, since it's the only critical point, right? When we're looking at odd roots, like the third root of something, we don't get the positive or the negative version. We strictly get the positive version, right? And so this is likely the only solution that we want for optimizing, in this case, minimizing this cost function. But it wouldn't hurt to kind of go through that process. And so if we do want to make sure that 79.37 is a minimum value for the cost function, right? We're likely assuming that it is, but we can also find the second derivative, right? And see what the concavity is at that value there, right? And so the second derivative, c double prime of v, comes from differentiating c prime of v. So that's going to be 1/10, okay? That's going to be 1/10. And then the derivative of, here, I'll put this on the side, ddx of 1/x squared, I guess I should say, is going to be -2/x cubed, right? And so applying that here, the negative with that negative is going to make it positive. So we're going to have v cubed on the bottom, and we're going to have 2 times 50,000 on top. And so that means we're going to have 1/10 plus 100,000 over v cubed as the second term, like so. And so now, if we want to see whether this is a max or a min, we should look to see at what the concavity of the second derivative is, right? And so let's plug that value in. So the second derivative evaluated at this critical point is going to be 1/10 plus 100,000 over. Now, you know that 79.37, that was really the cube root of 500,000, right? So that cube, right, no need to use a calculator there. That's the cube root of 500,000 cubed, right? Those cancel out conveniently. And so again, we don't need to use any kind of computing software. We just get 1/10 plus 100,000 over 500,000 is 1/5. And so we get second derivative that is 3/10, and that is a positive second derivative, right? A positive second derivative means we have a positive concavity of our function at that point, which means that we have positive, think smile, right? That means the concavity is like this. And so that means that our critical point, right, where the first derivative is 0, i.e. horizontal tangent line, this is clearly a minimum point, okay? Because it's at the bottom of that upwards concavity piece of our curve. And so, as we expected, a velocity of 79.37 minimizes our cost function for different velocities of the train. We checked it with the second derivative. Everything seems to stand to reason. And so we're done. Hope this helps. Again, rate of change is always akin to using the first derivative for that instantaneous rate of change. And then you can test whether any critical points are min or maximums using the concavity given to you by the second derivative. Okay. So again, I really hope this helps. If you guys have any similar questions that you'd love to see done in a video, please leave a comment below. And as always,